how you show well-posedness or what you need to worry about well-posedness. And then we'll move on to discuss this BSSN formulation of general relativity, which is a strongly hyperbolic formulation of it. I don't think we'll have time to prove well-posedness. We'll see. Maybe I'll leave it for next lecture, depending on where we get. But if you're interested, I can point you out to a reference where this is done explicitly and very nicely. So, and then we will move on to the final thing that I want to discuss before doing actual numerical simulations, which are the gauge conditions that we haven't discussed this so far, and we also need to know how to evolve the gauge variables, because they are also part of the system that you need to sort of show hyperbolicity. Okay? So today the last kind of PDEs that we want to discuss in terms of well-posedness are what's called partially reduced second order PD, second order system. And partially reduced stands for the fact that you only make a first order reduction in time, but you keep the second special derivatives explicit. Okay? So the kind of systems of this kind that we'll consider the following. Where this is a function okay, so this variable v is the time derivative of u, sort of. Okay, there's some mixing here in space, but that you should think of v as the time derivative. And then you have another equation for v, which can depend on the okay, so now this, you should think of this as an equation for the time derivative of v. Okay? So, let's say u is a n component vector, and v has m components. And the equations of general relativity in BSSN formulation are of this form. But in fact, we will consider some more general, case, which is the following, which is assume that this function v, I will not write all the dependents, is linear in the time derivative of v. Okay? So is of this form. So it can be also okay, and then there's another function w okay, so that will be the equation. So this is the form of, say, Lovelock like formulations of general relativity in this sort of ADM-like form. Okay, so in general relativity, this actually is linear. So this will be a linear function. Sorry, all of these will only depend on. Well, in fact, this will come with coefficient 1 in general relativity, but in Lovelock-like theories, you've got a more complicated structure here of this kind. So this can be multiplied by second special derivatives and so on. So Lovelock-like theories are like this, or Hordensky-like theories are like this. Okay, so that's more general than GR. Okay, so initial data for this system is okay. So this strategy is what we did before. So we assume that the t equals constant surfaces are not characteristic, so this matrix can be inverted. Okay, and we write the system as a first order system, and then one looks for what the conditions strong hyperbolicity imposes on the first order system, and then from this we obtain the conditions on the second order system, right? So the first thing that we're going to do is just rewrite these equations, so just invert this matrix and write this also as an equation for d, the time derivative of v equals to something. Okay, so if you do that, then one gets the following system. Is x to x u v, so x is AVV minus 1. Okay. So now we would do also a reduction in space. So we introduce a constraint. So we would say that Vi is di u. So this equation, then we would write it. So we would have this equation, and now by take a time derivative. Okay, and that will give us now an equation for this variable. So if you take now a spatial derivative of this and you commute the partials, then you get the evolution equation for these new variables. Okay. Okay, so now in this way, now we have a first order system, and then we would study strong hyperbolicity of this first order system. So what we did in first order systems, general first order systems, then is to look at the highest derivative terms, right? Because those are the terms that determine the strong hyperbolicity. So to do so, then we need to define the following matrices. VU, so that would be the highest derivative term in these equations are the coefficients of the second special derivatives. So this will give us so this will be part of the principal part. So now we need to identify the principal part, which the principal part are the higher derivative terms. So the higher derivative terms of this equation are the coefficients of the second special derivatives. And we need to look at the highest derivative terms of, and also this equation, because V is like a time derivative, right? So that's one time derivative and one space derivative, so that also counts as the same order as this one. So that will give us another matrix, which we will call it MVV. This is dx d t. Okay? So in this case, so the highest derivative terms in this equation, in the first equation, are, this is first derivative in space, so that the coefficient, so that will also appear in the principal part. And since we count this as a time derivative, then its coefficient will also be in the principal part. So bottom line is that the principal part, see, where can I write this? There. So principal part, so when we, again, remember that we considered the special Fourier transform, so you iterate the derivatives by the wave, the special wave numbers. So in this case, the principal part is okay, so this is the coefficient of the first special derivatives of in the U equation. That's the coefficient of V in the first equation. And again, whenever you have special derivatives, you iterate the special derivatives by the wave number. Then in the equation for V, we have a term with the highest derivative of U are the second special derivatives. So that's the coefficient. And then you bring down two xi's. And then these are the coefficient of the special derivatives of V, right? So these are the coefficients of the highest derivative terms in the equation. So strong hyperbolicity means that M is diagonalizable with real eigenvalues and a complete set of eigenvectors. Which you want them bounded, and depend smoothly on. Okay? So another way to think about this problem is to think of, in terms of, another way to think about this eigenvalue problem is basically the eigenvalue problem that one has to solve is the following. So this matrix L is nothing but this, and A would be okay. So if you group now the first order equations, if you group them in this form, so and you write the vectors in a covariant form, then the time derivatives would bring down the time component of the eigenvector, and then this is the matrix of the highest derivative terms, the highest spatial derivatives, the highest derivative terms in the equation, in the right-hand sides. Okay, so that's this matrix. So that's how this, and this would be, if you want, the covariant principal symbol. Okay, so bottom line, when you want to show strong hyperbolicity, you need to identify the principal part of the equation that is given by the highest derivative terms. When you have mixed space and time, then reduced first order in time and second order in space, then v, this variable v counts as having one derivative already. So that's why we have the coefficient here. That's a matrix multiplying the first derivative terms in the equation for u, and then you'll also look at the coefficient of the highest derivatives in u in the same equation. Okay, is this clear, the structure of these systems? And as I said, BSSN has precisely this structure. Okay, so that's all I wanted to say about strong hyperbolicity. And now we are going to move on to strongly hyperbolic formulation of general relativity, which is not. So we already saw the generalized harmonic formulation as a strongly hyperbolic formulation, and today I want to introduce the BSSN formulation, because that's the one that we're going to use in the numerical code, and that's also widely used in the community. Okay? So if there are no questions, I will move on. So the BSSN formulation stands for Baumgarten, Shapiro, Shibata, and Nakamura. So this was discovered in the late 80s by Shibata, and there are some two other names, Japanese names that I don't remember, that not usually include. So this was discovered in the late 80s by this Japanese group that were just playing around and looking for, other ways of evolving the Einstein equations. But at that time, they just did some simple numerical experiments, and well, they sort of realized that this sort of seemed to be stable, more stable compared to ADM. And then in the late 90s, independently, Baumgarten and Shapiro revisited this formulation, they rediscovered this formulation, and then they saw that it was clearly more stable than standard ADM, and people then tried to figure out why that was the case, and then it was understood that the reason why that was the case is because it was strongly hyperbolic, whilst ADM was not. So in fact, ADM was being used by the numerical relativity community for a long time, because that's the obvious way of casting the Einstein equations as an evolution system. But people just didn't know that it was only weakly hyperbolic. And in cases where you have special symmetry, like 1 dimensions or even 2 plus 1, then ADM is strongly hyperbolic in that case, right? But of course, in the late 80s, early 90s, people didn't do 3 plus 1 numerical simulations yet. So ADM kind of worked. But then it was only later when they started doing full-fledged 3 plus 1 simulations that they, ADM just blew on their faces, and they didn't know what was going on. And that's why then Baumgarten and Shapiro revisited this formulation, or rediscovered this formulation, and understood that this worked because it was strongly hyperbolic. Okay? But in order to finally succeed in simulating binary black holes, then this isn't enough. one needs to specify the right evolution equations for the lapse and the shift, and that's what we're going to do in the second part of today's lecture. Okay? Because as you saw in the ADM formulation, as we'll see in this formulation as well, the gauge variables appear in the equations of motion with second derivatives, and therefore the evolution equations for the gauge variables also affect the well-posedness of the overall system. Okay, so to motivate the BSSN formulation, I will start considering the Maxwell equations in written in terms of the scalar and vector potential. Okay. It seems fitting to talk about the Maxwell equations in this setting. So probably Maxwell, Yang Hui was telling us the other day that Maxwell actually came here and discussed with Faraday. So it's possible that these equations were written at some point here in this very room. So let's write Maxwell's equations in terms of the vector potential and the scalar potential. So you've got that's the vector potential, that's the scalar potential, and that's the electric field. And okay, and the magnetic field is the curl of the vector potential, so that's automatically divergence free, and then you've got the constraint that the divergence of the electric field is given by the electric charge density. Okay, so these are the Maxwell equations, and they are, in terms of structure of the equations, they are similar to the ADM equations. So in the ADM equations, so we have okay, so these are the ADM equations, and the analogy is that the vector potential is analogous to the metric in the sense that in the right hand side you've got one derivative of the you've got the field variable, like in this case the electric field, and in this case we've got the extrinsic curvature. Okay, you should count this as one derivative, right? The electric field is basically one derivative of the potential, and you've got one derivative of the gauge variable, that's gauge. So here you've got derivatives of the shift, and in the equation for the field, namely the electric field, the potential, the other variable appears with second derivatives, and you've got the matter term. So the metric appears with second derivatives in the Ricci, and then you've got also second derivatives of a gauge variable and the matter terms over here. Okay, and let me just write the Ricci because that's relevant. So recall that the Ricci plus, okay, so this is the structure of the Ricci, the highest derivative terms. They come with these mixed derivatives, then that's the derivative of the trace, if you want, and then that's the term that comes with like the wave-like structure, which is the same as this structure of derivatives here, and then we've got terms with Christoffel squared, but those lower order when we look at the well-posedness, okay? So that's why I'm not writing them explicitly. Yes.
Line of the last question.
Yes.
Is it partial derivatives or covariant derivatives?
It should be partial, but I'll just write it covariant so then you can, lower. So it could be, these are the Maxwell equations on a curved space, for example. So that you can take as covariant. It's irrelevant because all the Christoffels will be like lower somehow. And we're not coupling to the metric. So, okay. So, with this in mind, now, it turns out that the Maxwell equations, as written here, are only weakly hyperbolic. For the same reasons that the ADM equations are only weakly hyperbolic, and now we're going to see why and what are the possible ways of fixing the problem. And then we will do the same with the BSSN equation, with the ADM equations, and this will give us BSSN. So to see what's going on, if you take now a second derivative of the vector potential, and then if you take a second derivative, just do it, and then you use the time derivative, if you take a second time derivative of the vector potential, and then you use the time derivative of the electric field, then you get the following equation. Okay, so where I've used the evolution equation for the electric field. Now, what do we have here? So this term here, this is basically the wave operator acting on the vector potential, right? So that's good. So that's like box. Okay, so that's good, that's a wave equation. But the problem and the reason why this system is not well posed is because of this term. These derivatives have the wrong structure, and this messes up with the well-posedness. And the same is true with the Ricci. So this term is like a wave-like operator, but then you've got other mixed derivatives that screw up the well-posedness. Okay? So the problem, so there are different ways there are different possibilities of dealing with this problem. The first possibility is to fix the gauge. because after all, the gauge vector potential is a gauge variable, so we can choose it. So if this term is the annoying term, then we set it to 0. We can always do this by a gauge transformation. So we define this variable, and we set this to 0. And that's Coulomb gauge. Okay, and now, if you set this term to 0, now you get a wave equation for the vector potential, but this now introduces a constraint. Okay, so, and you can derive this constraint in the following way. So you know that this has to be 0. Now you can commute these derivatives. And now you can use this equation. And now we use, oh, I erased that, the constraint that the electric field has to satisfy. And now this gives us a constraint on the scalar potential. So basically, this tells us that now the scalar potential has to satisfy a Poisson-like equation. And that's analogous to choosing harmonic coordinates in general relativity, where if you choose harmonic coordinates, then if you write the Einstein equations in a covariant form, then you essentially throw away all these terms that have the wrong structure, and you are left with something which is like a wave equation for the spacetime metric. Okay, and then you've got the constraints, which are that the these spacetime coordinates have to satisfy themselves wave equations. Okay, so that's option number 1. Option number 2 is to just work directly with the gauge invariant quantities which satisfy wave equations. So, and then write those as, say, for example, first order equations. So for example, in this case, this would correspond to, let me leave this. So you do it in the following way. So if you now take a time derivative of this equation, you have that the second time derivative of the electric field, because these are just, you can just commute the time derivative through this equation, then you get a time derivative of the vector potential, and then you use this equation to calculate the time derivative of the vector potential. And then if you do that, then you see that these terms are such that everything sort of cancels out. In particular, those terms cancel. Oh, actually, I'll just write it explicitly. That's correct. Okay. Then you also need to use, if you use the constraint for the electric field, you can just trade this by a special derivative of the charge density, and the mixed derivatives, because this just acts on a scalar field, all the mixed derivatives cancel, and you end up with a wave equation for the electric field. which probably Maxwell wrote in this very room. Okay, so this term comes from this term using the constraint. So now this is a gauge invariant, this is an equation for the gauge invariant quantity, namely the electric field. Okay, and this is clearly a wave equation, so that's well posed, and you can just go about and solve it. So one can derive in vacuum, or well, in fact, it's not only vacuum, for general relativity by using the Bianchi identities. You can show that the Bianchi identities can be a lead to Maxwell-like equations for the electric and magnetic components of the Riemann tensor in 4 dimensions. So these are also gauge invariant quantities. I will not derive those, but that's the analog of this option. But this has not been used in numerical relativity. But yeah, so these lead to EM-like equations for the curvature. For the in 4 dimensions, you can decompose the Riemann tensor into electric and magnetic components, and then, or the Weyl tensor in vacuum, and from the Bianchi identities, you can derive the corresponding equations. So that's option number 2. But as I said, this has not been used in GR. So option number 3, sorry, is the following. So recall that we said that one of the issues that we had was basically, so this is the offending term in the evolution equation, so we want to get rid of this thing. So, and we impose a gauge, which is Coulomb gauge, which is to set this to 0. So the other option is to now promote this gamma to a new variable and derive an evolution equation for it using the other evolution equations. Okay? So, new variable. So if you promote this to a new variable, then you use, sorry, this I can erase. Now I can erase this. So if you promote this to a new variable, then this equation simply becomes okay? So that's the other equation, and now we have to derive an evolution equation for this variable. So we just take a time derivative. So that will be okay. And now here comes a critical thing. So now we use the constraint for the electric field to get rid of this term. And therefore, by using the constraint, what we are doing is we are changing the principal part of the equation, right? Because E counts as one derivative. So here we are taking the derivative of the field. So that would count as a 2 derivative at the same order as second special derivatives. and now we're using the constraint to get rid of this term, and we write it as okay? So now we got rid of this term using the constraint. And this is critical. This is critical because, as we shall see very shortly, if the constraints are satisfied, this formulation is entirely equivalent to the previous one. But of course, if the constraints are not satisfied, then it's different. So the constraints are just you adding zeros, and you can add zeros to the equations after all, right? But this formulation has a different property. The constraints propagate in this formulation, and while the constraints do not propagate in the original formulation. And this is critical. And it's critical in particular in GR. Because when you do numerical simulations, you will always have constraint violations, basically because you approximate the derivatives by some discretized version of the derivatives. So this inevitably is an approximation. So this inevitably generates constraint violations. So those constraint violations, if they do not propagate, then for a nonlinear system, this is a problem because then they accumulate and they actually grow exponentially, or in fact faster than exponential, and then your simulation blows up very quickly. So having constraints propagating at some finite speed is critical to ensure numerical stability, because those constraint violations can propagate and eventually exit the computational domain. So let's see the constraint propagation properties in this formulation and in the previous one. Okay, so we have a constraint here, which is that the divergence of the electric field, okay, and this has to be 0. We want this to be 0. So now let's see how this constraint propagates. So if you take a time derivative, now we use this equation, we commute the derivatives. Okay, so we can now commute these derivatives and use this equation to compute the time derivative of the electric field, and then we will hit this with this derivative. Okay, and one equation that I forgot to write is the continuity equation. So that's the continuity equation. And you can see that this is 0. Okay? So it means that in this formulation, the constraints do not propagate. Okay, they have 0 speed. And this is a problem for the reasons I pointed out. However, we'll see that in the other formulations, constraints do propagate. So in deriving this equation, okay, one can actually, so is it clear that these constraints don't propagate in here? Okay, so let me just revisit this. So in deriving this equation, okay, as I said, you can always add constraints to the evolution equations, and you can add them in, with arbitrary coefficients. After all, you're just adding zeros, right? So suppose that now you add to this equation some constant a multiplying the constraint. Okay, you can always do that. So if you do that, then the equation that you end up getting okay? So if you set a equals 1 is just what we did before. Okay? So now you take this equation. So now we want to compute, again, the time derivative of the constraint. Okay? And now, to calculate the time derivative of the electric field, we're going to use this equation. Okay? And if we do that, then one arrives at the following equation. Okay? That's using this equation. And here's where the magic comes. So clearly you see that now the constraints have a non-zero time derivative. But to have a better understanding of how they propagate, it's useful to take another time derivative of the constraint. And if you do that, then, and you take a time derivative, you commute the time derivative here, you use the evolution equation for A to take a time derivative here, and then the time derivative will also act on gamma, and for the time derivative of gamma you use now this equation here, okay? And if you do all of that, all terms cancel, and you arrive at this equation. Okay? Everything cancels. Feels like magic, but magic happened in this context. So this shows that in this formulation, the constraints propagate like a wave equation with a certain speed a. For a equals 1, the speed is the speed of light, but these are constraints, these are unphysical, so they can propagate at whichever speed you like. It need not be the speed of light, and there's no problem in causality. There's just finite speed of propagation. Physical effects, namely the evolution of the electric field, will continue to propagate at the speed of light, but constraints can propagate at whichever speed you like. And that's not a problem. The point is that now constraints have a finite speed of propagation, so if you have constraint violations in your system, those constraints will just move around and eventually exit the computational domain. For the Maxwell equations, the fact that the system is linear, having constraint violations is not such a big deal, but for nonlinear systems, having constraints that do not propagate can be fatal for the stability of the simulations. Okay? So now we are going to implement this strategy in the ADM equations, and we'll introduce a new variable which will basically help us dealing with the structure of the second derivative terms in the second special derivatives, and we'll promote this variable to a new evolution variable, and this will turn the system first strongly hyperbolic, and at the same time, because in deriving the equation in deriving the equation, so that's the key point. In deriving the equation for this variable, we use the constraints. So this is critical in giving the constraints a finite speed of propagation. So we'll use the same for the Einstein equations. Okay? So this means that you can derive, if you want, infinitely many formulations of the Einstein equation by just adding arbitrary combinations of the constraints to the evolution equations. This at the continuum level is inconsequential because you're just adding zeros, but because when adding those constraints, then you can change the second derivative structure of the equations, turning them, first of all, strongly hyperbolic, and secondly, giving finite speed of propagation to the constraints, which is critical in numerical simulations. Okay, so that's the idea.
Sorry, I have a question.
Sure.
In this formulation, how many initial data we have to specify?
The usual initial data, because you know that initially, so you specify initial data for A, and then you calculate the initial data for A from here. Okay, so it's the same. So you're not changing, in a way, the propagating degrees of freedom. You're not changing the number of physical degrees of freedom. Okay, so now, after this detour, I wanted to derive the BSSN equations using exact, but so first of all, I'm not going to do it for two reasons. One, because I didn't have time to prepare the notebook. That's reason number one. And reason number two is because today I want to make sure that we have enough time to discuss the gauge conditions, because then we can dedicate the last two lectures to the numerical simulations. And in fact, you don't need mathematical to derive the BSSN equations. It's just, it's just a calculation, which you can do by hand. Okay, so the idea is, first of all, we'll simplify, introduce a new variable to change these two derivative terms, the special derivatives. To change, I would say replace some second special derivative in Ricci, the special Ricci. And the other thing that BSSN does is separates, do conformal transformation of the induced metric and extrinsic curvature. And the reason behind this is twofold. In doing that, one wants to separate the transverse degrees of freedom, which are the ones that carry the physical ones, from the longitudinal, which are gauge. And second, that you achieve by doing that is hide certain singularities in the conformal factor. So more precisely, you can construct initial data containing black holes, and the way you do it is by making the conformal factor singular in a very specific way, and that gives you initial data for black holes, like binaries in a binary and so on. So the only singular variable turns out to be the conformal factor, whilst all the other variables remain regular. That improves numerical stability. That works well in the 4-dimensional setting, but in higher dimensions, that no longer works. So it turns out in higher dimensions, when you have black hole spacetimes, then all variables have singularities that you need to deal with, but that's not a concern for us here. Okay. Yeah, let's just finish this part and then we take a break and we move on to the gauge conditions. So what you do in BSSN is you introduce a conformal rescaled metric. Okay, so that's the physical spatial metric, and you introduce a conformal factor, and this conformal factor is basically where this is the determinant of the spatial metric, and this is the determinant of a reference metric, which we will take to be Minkowski space in Cartesian coordinates, so this is just one. Okay, so you should think of this as a constraint between where you introduce now a variable, which is basically the volume, the spatial volume of the metric. Okay, so now the determinant of the rescaled metric is 1. And that's a constraint. Okay? And it turns out that the equations preserve this constraint. So that's the rescaling. And now this is a new variable. And because you know the ADM equation for gamma, the induced metric, then you can derive the corresponding evolution equation for this trivially. And you can derive the corresponding evolution equation for the rescaled metric, okay, from the ADM equations. Then you do the same conformal transformation for the eccentric curvature. So you take the traceless part of the eccentric curvature and you rescale it by the same conformal factor. So that's so this part is the traceless part of the eccentric curvature, and now we rescale it by the same factor. Okay? And again, ADM equations give you the evolution equation for the eccentric curvature. So from this, by taking the trace, you get the evolution equation for the trace of the eccentric curvature, and from then you do the conformal transformation, you get the evolution equation for this. Okay? So far, all you've done is basically a conformal transformation of both the induced metric and the eccentric curvature. Okay? And you derive trivially equations for them from the known BSSN equations. I will not write them down because I'm just writing down the equations, and you can just find them in references, and it will take me like 5 minutes to write down these messing equations. Just to say that if you try to do that, then you realize how much more complicated are the BSSN equations compared to the equations that you get in generalized harmonic coordinates. Okay, it's like at least 2 orders of magnitude longer. And that matters when you do computations, right? Because you have to do many more operations to calculate the right-hand sides. So that has an effect. Now the key point I want to make is that recall that in the evolution equation for actually I need I'll just write a portion of the equation for this, which you, as I said, you derive from the known ADM equation. So you've got terms like this. And you've got other stuff, okay? So TF stands for trace free, Okay? So you just take the trace-free part of the evolution equation for the concentric curvature and you rescale it. Now the problem, now we've done a conformal transformation. So now you need to calculate Ricci. This term was the one that was causing problems. So now when you do a conformal transformation, that's the Ricci of the special metric, and you can compute it by the Ricci of the conformally rescaled metric, and then you get another term which has second derivatives of the conformal factor. You can find the formulas in the references. But the term that now will cause problems is this one. That's the one that will have second derivatives of the conformally rescaled special metric. Okay? So, and here's the key trick in BSSN. Now, we promote this combination So these are the Christoffel symbols of the rescaled metric. And you do this contraction just as we did in harmonic gauge, remember? But now this is only the special metric. And you promote this to a new variable. And it turns out that because the determinant of this is equal to 1 in these coordinates, that's equivalent to this. Okay? So now this becomes a constraint, and this becomes a new variable, and we use this variable in the computation of Ricci. So now you write Ricci in the right-hand side in this form. But in fact, it appears somewhere else like this, and then there's another term, and other terms with gamma squared, Christoffels. Okay, so now that's how you compute the Ricci on the right-hand side, where now this is an evolution variable. Okay, this is an independent variable, and this is the key point. Right? So when you write the BSSN equations, you have to keep this term. Although, because now you've changed the two derivative structure of the equation, and this is what gives you well-posedness. Okay? So there's some, let's say skeptical students that say, oh no, this is like a constraint, it can be anything. Right? No. This change, you cannot alter the computation of Ricci in a numerical code. You have to use the evolved variable. Otherwise, the system is not strongly hyperbolic and therefore not well-posed. Okay? So that is now a new variable. And it's critical to keep it like this. This term is not so important. And in fact, in some codes, some people use this combination here. And you can see why. That's largely inconsequential because that's a lower order term. This term does not affect the principal part. So you can do pretty much whatever you like. But you cannot change this term. Okay? So now we've got this variable, and now we need to derive an equation of motion for it. So, and that's the sort of, so you would do, yes?
So the third term, is it gamma tilde or just gamma?
Yeah, that would be gamma tilde. That's basically the Christoffel of the special metric with one index lowered.
And you lower it using
you use gamma tilde, yes. Okay. Yes. So that's the equation of motion for gamma. Okay? And here's the thing. So you get the ADM equation for this, that when you write it down, in fact, you can see that it has this structure. So remember, the ADM equation for the metric gives you extrinsic curvature, so now it will give you the rescale extrinsic curvature plus other terms, So this term will give you, now you'll substitute the time derivative from the evolution equation for gamma tilde, which will then give you something that looks like this. Actually, minus 2 alpha and other terms. And recall the momentum constraint. The momentum constraint equals, I think, matter 8 pi ji. Okay, that's a momentum constraint. If you now do the conformal rescaling, then the momentum constraint tells you what this derivative is. So now you use the momentum constraint to calculate the right-hand side of the equation for gamma tilde. Okay, so that's the same thing that we did in the Maxwell equation, where we used the constraint for the electric field to eliminate the special derivative of the electric field. So now we use the momentum constraint rewritten in terms of the rescale variables to eliminate the special derivative of this. And then you, after you do that, then you get something which is a mess. But now, how can I write this? So this term will have now A multiplying derivatives. So A appears with no derivatives now, if you use the momentum constraint. I'm not going to write the equation because it's a mess, but you get A, which appears linearly, multiplying certain terms with first derivatives, and you get terms with second derivatives of the shift. Okay? So that's the structure of the equation, and it's a mess, but you can find it in the references. Okay? So that has the exact same structure as the partially reduced system that we discussed. So in order to now show strong hyperbolicity, we need to find suitable evolution equations for the lapse and the shift, because as you can see, they appear with up to second special derivative, so they contribute to the principal part. Okay, so what do we achieve with this? By defining this variable, we change the principal part and of the equations, and critically, we've used the momentum constraint in deriving the evolution equation for this variable. So now you can show that in ADM, both the Hamiltonian and momentum constraints do not propagate. They have zero time derivative, and we showed that in the previous lectures. So that's bad. That's bad for numerical GR. I mean, theoretically it's fine because it shows that if they are satisfied initially, then they will continue to be satisfied. They have zero time derivative. But when you have constraint violations, then that's bad, because then they'll just sit there and they accumulate with time and they will blow up. But now in BSSN, you can show that the momentum constraint propagates, has a finite speed of propagation, so constraint violating modes will eventually exit the computational domain, and that's one critical aspect of stability. The Hamiltonian constraint does not propagate in BSSN, but it turns out that this is not a problem in practice. And I cannot tell you why, this just happens to be the case. But there is an improved version of BSSN, which goes under the name of CCZ4, in which the Hamiltonian constraint is also given a finite speed of propagation. So that of the scheme turns out to be more stable. And in 4 dimensions, it's not a huge improvement, but in other settings where you've got larger constraint violations, like high dimensions or ADS, then that turns out to be superior. Okay, so let's take a break. So gauge conditions amounts to choosing coordinates, and since all of you are experienced doing calculations in GR and so on and so forth, you know that there are good coordinates and bad coordinates, right? So for example, Schwarzschild coordinates break down at the horizon, so you need to find good coordinates that can allow you to sort of cover the interior of black holes, for example, right? So this is just all about choosing good coordinates that allow us to do two things. So we need to avoid coordinate and perhaps and physical singularities This latter part is somewhat, I would say, optional in the following sense, because if you have black holes, then you know that once you cross the horizon, all the information, all modes necessarily point inwards. So in principle, if you have black holes, then you can excise the interior of black holes. Okay, so, and in that way you would avoid physical singularities, and the way in which you avoid physical singularities is somewhat independent of your choice of coordinates. That's what you do in generalized harmonic coordinates. But as we shall see today, one can choose coordinates such that they do not hit physical singularities. But one key point is that you need to avoid the formation of coordinate singularities, because coordinate singularities for numerical computation has in some sense the same effect as a physical singularity, which is that the code crashes. Okay? And the second thing that you need to think about is that the so the coordinates that you choose should not spoil the well-posedness of the overall system of equations, because as we saw, the gauge variables, namely lapse and shift, enter with second derivatives in the equations of motion, so they will contribute to the principal part. Okay, so that's the second thing to bear in mind. And as I said, we identify the lapse and the shift as our gauge variables, because they parameterize the normal vector to the hypersurfaces, so that tells us how these hypersurfaces are embedded in the full space-time. So that's where this gauge freedom comes from, but it's also reflected in the fact that the Einstein equations don't give evolution equations for the lapse and the shift. We have the evolution equation for the induced metric, the extrinsic curvature, and then you've got the constraint, and this exhausts all the Einstein equations. Right? So the fact that the Einstein equations do not provide evolution equations for the lapse and the shift is just a reflection of the fact that these are just free variables, coordinates. Okay, so first we're going to discuss the lapse. Okay, the evolution equations for the lapse. So, the evolution of the lapse. So there are several options that one can think of. So one is to prescribe the lapse as a function, as an a priori known function of space and time. Okay? Yeah, you can do that, but I would say good luck with that, because if the space-time is highly dynamical and you form black holes later on, then it's not at all clear that your original prescription will be able to avoid formation of singularities. Okay? So if you can do that, please let me know. Second option is alpha, specify the lapse as an algebraic function of the other variables, of the dynamical variables. Okay? And this sort of makes sense because, okay, if you prescribe the lapse as a fixed function, and we'll come to that in a specific example, which is sort of well motivated, then you prescribe this initially, and then regardless of what the spacetime does, then the lapse will be that function. So we will not be able to react to sort of the dynamics of the spacetime. Whilst this other option seems more sensible, because if you prescribe alpha as an algebraic function of the evolution variables, then as the evolution variables change, because you form a black hole or whatever, then the lapse will also react to that. So that sort of makes sense. But we'll see that this also there's no known way to make it work in practical examples, but that's another option. Third option is give an evolution equation alpha as a solution of an elliptic PDE that imposes a geometric condition. So as we shall see, there are certain geometric conditions that implement in practice the fact that you don't have singularities, and those result in an elliptic equation for the lapse that should be satisfied on each hypersurface, on each time equals constant hypersurface. So you could imagine that you have all your variables, you are on this hypersurface, then that gives you solve an elliptic PDE that gives you the lapse, and then you step forward in time. So that's a way that would work if this geometric condition is such that it avoids singularities in the computational domain. And this is possible. In practice, this is not so, because elliptic PDEs are expensive to solve in practice. So numerically, these elliptic PDEs involve inverting matrix, which is the matrix is basically built from the discretized derivatives in your equation. And you can imagine that in a black hole spacetime with a huge computational domain, with lots of resolution in certain regions near black holes, these matrices are effectively huge. So that is practically, it's not practical to implement, right? So you would spend like more than 90% of the computational time solving this elliptic PDE. So that's not practical. So final option is prescribe an evolution equation for the lapse okay, and one can actually do that, prescribe a hyperbolic equation for the lapse such that this solution, this equation evolves the lapse towards solutions of these elliptic PDEs. So that's a way in which you dynamically implement these geometric conditions, or something which is close enough to this geometric condition. And of course, evolving a variable forward in time is cheap computationally. You just need to store the information of, say, in the previous time step on the one before, and that's it. You just use those previous values to, calculate what is the next value. Right? So that's cheap. And we'll see this in practice when we do numerical simulations. Like in all time evolution schemes, you use the solutions at the previous time steps to calculate what the time derivative is and therefore step forward in time. So that's computationally cheap. Right? So that's the option we're going to go for in practice. Okay? So let's consider the following. So one way to motivate the choice of labs is the following. So if you consider a hypersurface, and there's a volume here in this hypersurface, volume V, okay, and we want to look at how, so this volume V will be of this computed as just a volume on this hypersurface, right? That's on the induced metric. And we want to consider how this volume changes, right? And we want to consider changes in this volume such that the boundary stays constant, okay? So that's the problem we want to consider. So you can show that the time derivative of the volume is just the variations of this volume. It's just the variations of this form, and you can calculate this that's just okay, that's this formula that you know. Okay, so we can use the ADM equation for the induced metric to calculate the variations of the determinant, right? And if you do that, and you impose that the boundary of this volume is fixed, then you can show that these variations of this volume are basically computed by the trace of the eccentric curvature. Okay? So let's keep this in mind, because this will play a role in terms of the sort of choice of labs. Okay. So now let's look at possible what observers see, right? So let's consider observers that move along n, this normal vector to the hypersurfaces, okay? And now, in general, these observers need not be free falling, right? They'll be accelerated because we are in a gravitational field, so you know they need not move on geodesics, for example. So you can compute the acceleration of these observers by just this formula. So if this is a geodesic, right, this will be 0 if you choose an affine parametrization, and the acceleration just measures the failure of this vector to be tangent to a geodesic. Okay, and you can compute the components of the acceleration, and you can show that the components of the acceleration are just given by the derivatives, special derivatives of the labs. Okay? So another important quantity is that you can see that the variations of this volume, of the volume elements are given by the trace of the eccentric curvature. But in fact, the variations that these observers see is also computed by the divergence of this vector. So the divergence of this vector basically measures the changes in the volume elements that the observers with tangent that move on curves tangent to this vector see. Okay? So now you can say, well, if one can say, okay, now let's choose a slicing such that these observers move on geodesics. So that's called geodesic slicing. And you can do that by simply setting lapse to 1. So if the lapse is set to 1, then clearly the acceleration vanishes. So now these observers, whose vector is tangent to n, move along geodesics. And that will be the option number 1 that we just discussed. Right? This would fix the lapse once and for all. But now you see the problem. The problem is that these coordinates will become singular. And the reason is that intuitive, because if you are in a gravitational field, the free-falling observers will be focused. So there's nothing that will prevent those observers from colliding with each other. And then when they collide, then this will result in a coordinate singularity, because the coordinates will no longer be 1 to 1. Okay? And another way to see this is that you know that the volume elements that these observers see are related to the extrinsic curvature, to the trace of the extrinsic curvature. Okay? That's seeing how the trace of the extrinsic curvature controls the rate of change of the volume elements seen by these observers. Now, if you use the ADM equations, you can look at the evolution of the trace of the extrinsic curvature, and it's given by this equation. Where you use the Hamiltonian constraint to eliminate the trace of Ricci, the Ricci scalar. Now, if you choose this slicing, then this term is 0. And then this shows, so this is just the derivative. If you now bring this term to the other side, and you set this to 0, now this is just the derivative of the extrinsic curvature along this vector. Okay? And now this is equal to this quantity. This quantity is positive, right? This is just the square of a special vector, and this is positive if the strong energy condition holds, which is just what normal matter should obey. So then you see that this equation tells us that that with this choice of coordinates, the trace of the extrinsic curvature just grows without bound. Right? It always increases, and the variation of the volume elements is the integral of this with a minus sign. So it means that the volume elements seen by these observers shrink. So they will eventually become 0, and that's coordinate singularity. Okay, so this shows that geodesic slicing is a poor coordinate choice. And the way this happens is because the volume elements shrink to 0 size, and that's a coordinate singularity. So this also indicates us a way forward. A way forward would be, okay, so since the trace of the extrinsic curvature controls the volume elements that observers see, then if we don't want those volume elements to go to 0, because that's a coordinate singularity, then perhaps what we could do is to find an equation such that this doesn't change. Therefore, if you have the extrinsic curvature to have 0 trace. So that's called maximal slicing. Maximal slicing that's impose k equals 0. So it's called maximal because you can show that the volume elements, if you impose this condition, are maximal. So this maximizes the size of the volume element. It's like the soap bubble type of problem. Okay, I'm not going to show this, but you can see that the time derivative of the volume elements is 0. It shows that this is at least an extremum. So if you impose k equals 0, the time, if you impose that this is 0, the trace is 0, then from this equation, you see that this gives an elliptic equation for the lapse. Okay? So that's option number 4 that we discussed earlier on. So on each spatial hypersurface, then now you have to solve this elliptic equation for the lapse, subject to suitable boundary conditions, which is an issue. And this would impose that the trace is 0. Okay? There are some caveats. One is a practical one that I already mentioned, that this is expensive to do in practice. But also in cosmological spacetimes, you can impose this condition, right? For example, in de Sitter, the volume elements just keep growing, right? Because the universe is expanding, so that this condition is incompatible with cosmological spacetimes. You can relax it, and instead of choosing this to be 0, you can choose it to be a constant. Then that will be okay for cosmological spacetimes. And in asymptotically flat spaces, this will be okay for asymptotically flat spaces. But if instead you choose this to be a constant, then this would give you hyperboloidal slices. Slices that reach null infinity instead of being pinned at special infinity, which is something which is of interest if you want to study gravitational waves at null infinity. Okay, so that's useful, and I want to emphasize that with this slicing, then you clearly avoid coordinate singularities because the volume elements are just maximum, stay finite all the time. Okay. Now, one way to see what happens is that one can look at solutions to this equation, again in some like simplified settings, and when you do that, and you look at what solutions to these equations look like, then you can show that in regions of high curvature, then the lapse behaves like some, right? That's essentially the radius of curvature behaves like this in the regions of high curvature. This is just from studying solutions to this equation. So this tells you that solutions to a maximal slicing corresponds to the lapse being going exponentially to 0 in the regions of high curvature. Okay, that's called the like vanishing, what's the name? Vanishing of the lapse. And that's something that we will see in practice. Okay? So one way, the message here is that good coordinates that prevent the volume elements from shrinking to 0 size correspond to choices to regions in where the lapse vanishes exponentially, or in fact vanishes. So in order to see in practice, in cases, what happens for these slices, when you for example study gravitational collapse and you choose maximal slicing, so if this is like space and this is time, and you have matter collapsing and forming a horizon, so at some point there's a horizon. Let me see, form a singularity, so singularities are dangerous, so I'll use red for the singularities. And you form a horizon, so the event horizon will appear somewhere there, okay? And now you look at what the slices do, and far away when the gravitational field is weak, then those maximal slices will just be like pretty much flat, but as matter collapses and forms a black hole, then you see that the lapse is starting, they start doing like this. So the lapse is starting going to 0 in these regions, and basically all these slices are pinned and that's the key point of these slices. They are pinned, the place where the lapse goes to 0 is at some finite coordinate distance from the singularity. Okay? So these slices avoid the singularity, and avoid the singularity in this way. So first they are pinned at some finite distance of the singularity, and in this region here, the lapse goes to 0. So for example, for Schwarzschild, for maximal slices, you can see that this point where the lapse goes to 0, for Schwarzschild, this is like 3m over 2. So that's a finite distance from the singularity. And the way these avoid the singularity, these slices, is if the lapse goes to 0, it means that time freezes. Right? In the ADM metric, alpha multiplies the dt squared. So the lapse going to 0 means that inside these regions of high curvature, time freezes. Okay, so you cover a portion of the interior of the black hole. You don't cover all of it, because there's this region over here that you never reach. And it does so by time freezing. Right, so time stops inside black holes in these slices. But then you see that there's a problem. The problem is that indeed time freezes in the interior, but outside time continues to evolve. Right? So that's kind of weird. So you've got a region in which time stops, but then outside time does not. So one problem is that you need to account for both. So this implies that the slices stretch outside black holes. Okay, and this means that the radial gradients of the metric become very large near black holes, and eventually this is bad for numerics because this will cause the code to crash. Okay, so that's not that's not ideal, right? So one way in which you deal with this is by adding advection terms to the lapse evolution equation. This will keep this stretching to some extent. And the other problem is that in order to impose this condition, we need to solve an elliptic PD, and that's not doable in practice. Okay, so the idea is to now come up with hyperbolic equations for the lapse that, in some sense, do the same thing as these maximal slices. Right? You get slices that are pinned somewhere inside black holes, which will not be this point because that's what you get for maximal slices. But as long as those slices are pinned at some finite coordinate distance from the singularity, that's all you need, and they will all lead to freezing of the lapse inside black holes. Okay, so we need to control the stretching. So to see what kind of evolution equations, hyperbolic evolution equations one gets for the lapse, let's take a look at harmonic coordinates. So in harmonic coordinates, okay, so you can see that harmonic coordinates imply that the lapse, and here it's minus, I will call all of these total derivative. Okay, this is what harmonic coordinates give you for the lapse. And if you use now the ADM equations, you can see that this corresponds where this okay. So in this coordinate, you see that this stays constant. This is really not ideal because both, you see that in maximal slices, the lapse goes to 0 near the singularity, but also the volume may go to 0. That's how we identify a coordinate singularity. So in this case, it's not clear that that harmonic slicing will save the day. And in fact, we'll see shortly that this is just a marginal case. We can just marginally avoid singularities, but that's not good enough for numerics. So one could say, okay, one could impose an algebraic condition of this form, right? Fix the lapse in terms of the volume element of the metric, but you can see that this gives rise to singularities. That's not good. However, it was shown experimentally that a condition of this form managed to avoid singularities to some extent. And that's the famous 1 plus log slicing. And that's singularity avoidance. That's good for singularity avoidance. That, again, you can show that this can lead to an elliptic equation. Sorry, that's not true. But now we want to implement this as an evolution equation for the lapse. And this is part of a wider family of evolution equations for the lapse called the Bona-Masseau family. In English it's pronounced Bona-Masseau, but both Bona and Masseau are from Mallorca, so in Catalan is Bona and Masseau, but anyway. So that's a family of evolution equations for the lapse, which is of this form. Okay, so this involves the Lie derivative of along the sheet directions. That helps with stretching. This prevents slice stretching. And now we want to find a condition that basically avoids singularities, where this is an arbitrary function of the lapse. Okay? So f equals 1 is harmonic gauge. So you can see f equals 1 is harmonic gauge. And f equals some number divided by alpha. You can then integrate this equation, and you can see that the general solution is of this form. Okay, well, this is just an arbitrary function which you can set to whatever you like, and if you set n equals to 2 and this to 1, that's 1 plus log slicing. Okay. I do not have time now because of lack of time, but you can show that this gives a hyperbolic equation for the lapse. That's if you take now a second time derivative of the lapse and you use the ADM equation to calculate the time derivative of the trace of the extrinsic curvature, you can show that this gives you a hyperbolic equation for the lapse, so that's compatible with the well-posedness of the overall system. Okay, so now the last thing I want to show you is that this avoids singularities. Okay. Is it clear so far? So now let's see how this avoids singularities. Let me just skip the okay, so we've got this equation that's hyperbolic, so that's okay. So now to see what kind of how we avoid singularities, let's assume that the volume element shrinks near singularity, shrinks in this way, where tau is the proper time, and tau is the proper time of formation of the singularity. And you can show from the ADM equations that this power is in fact 1. Okay, so indeed, near singularity, quite generically, you can show that that's how the volume elements behave. But what we want to do is to avoid singularities. So you can compute, using the ADM equations, how, using the fact that this is related to the change of the volume element, then the change of this volume element using this gauge evolution equation for the Bonamasso class of gauges gives you this equation. So the changes in the volume elements is given by some function of space times the exponential of this thing. Okay, so now the whole point is whether this stays finite or not as you approach the singularity. And there's something else to need to bear in mind, is that this is the time, the proper time to the singularity, but what matters when we do numerical evolutions is the coordinate time. So the coordinate time that it takes to get to the singularity, assuming using the ADM form of the metric, is this, right? Because remember, in the ADM form of the metric, you have dS squared is minus alpha squared d tau squared, so that's basically d tau squared, okay? So, if this integral is finite, then it means that it will take a finite coordinate time to reach a singularity. That's bad, right? So, if the proper time can be finite, but the coordinate time can be infinite, then that's good, because in any finite simulation, you will never reach the singularity, but you may still get exponentially close. But it could be that this time becomes infinite before you reach the singularity, and that's the ideal case, where you will avoid the singularity. So if you choose a function of this form, okay, then you can see that this volume element will behave as the exponential okay. So if alpha is negative, if this power n is negative, then this exponential will remain finite, which means that in this slicing, the volume elements will always remain finite. So you will avoid the singularity. And the Bonamasso family of gauges, alpha is minus 1. Okay? So this shows that in this gauge, the volume elements will remain finite at all times. And in fact, then you can show that this would become infinite, the time the formation of the singularity. And in fact, it will become infinite before you reach the singularity. Okay? The case n equals 0 is a borderline case, and I don't think we have time for this. We can do that in the next lecture if you are interested, but it suffices to say that harmonic gauge is a case in which you can show that it takes infinite coordinate time to reach the singularity. And in that case, in practice, is just not good enough numerically. So the optimal case, so just to finish this, the optimal choice of n is this. N cannot be too negative, and the reason why this cannot be too negative is because you also want alpha to be in some sense, to be such that you avoid the singularity, but also you want the time that alpha, the lapse freezes. So you also want this near the singularity. you also want that the time derivative of the lapse near singularity is 0, right? So the lapse stays constant, freezes. That's what this property that we saw earlier. And you can show that with this behavior, then the time derivative that follows from the Bonamasso evolution equation, that the time derivative of the lapse will also be 0 near the point where the lapse collapses, as long as n is larger than -2. So 1 plus log slicing is right in the middle of this sweet spot. Okay, so 1 plus log slicing achieves two things. One is that the volume elements remain finite at all times, so there's no current singularity, and second, the lapse freezes, so there's no time evolution inside black holes. Then stretching of the slices near black holes is taken care of by the advection terms in this equation. And this is a hyperbolic equation which has, I didn't show it, but the propagation speed that this equation gives rise to depends on the choice of this function f. So the gauge modes will not necessarily propagate at the speed of light. Only when f is 1, then you get, that's harmonic gauge, then you get that the gauge modes propagate at the speed of light. So for f of alpha different from 1, then the gauge modes propagate at speeds which can be larger or smaller than the speed of light, depending on your choice of f. That's fine. After all, these are not physical modes, so they can propagate at whichever speeds they have to. But that's not proper. Physical effects will continue to propagate at the speed of light. Okay, next day we will do quickly the evolution for the shift, and then we will do some numerical simulations, and I think that will be it. And one thing to look forward, one thing that we will be looking at the numerical simulations is precisely we will see how the lapse collapses in a certain region of the space-time, and which means that we are evolving towards these slices. Okay, then I'll see you on Thursday.